Hello, everyone. This is Lydia Olander from Duke University and the National Ecosystem Services Partnership. Welcome to our webinar today. I just want to give a few quick notes about the webinar. We will have participants muted during the call so that we don't have interruptions. And then at the end, we will take questions. So if you have questions or comments, you're welcome to type them into the chat box. And Sarah, at the end of the call, will help read those questions out and help that conversation move forward. And if necessary, unmute people so that they can have a back and forth with the speaker. So just want you to keep that in mind for the presentation. So please feel free to type your questions into the chat box or let Sarah know that you have one and would like to be unmuted. So I'm just going to do a quick introduction before we get started. Our speaker today is Emily Pindilli. And I'll give an introduction of her in a moment. I just want to note a few updates from the partnership. We have some new resources we've been posting online. We've been doing some ecosystem services mapping and methods development right now for the southeastern states, and we have 2 of these online so far, one on recreational birding and another one on conservation restoration priorities for wild pollinator habitat. So if you're interested in that, that can all be found online, and the data is all available on Sciencebase from USGS. So next, our speaker, Emily Pindilli, is an economist and the Natural Resource Economics Theme Lead at the USGS and USGS Science and Decision Center in Reston, Virginia. She specializes in economic and policy analysis to support energy and environmental projects. Her portfolio includes the value of scientific information, ecosystem services assessment and valuation, methods to integrate multidisciplinary analysis to support land use decision-making, life cycle analyses of resource development, conservation, and environmental markets. I've been seeing Emily's work on ecosystem services with a number of different agencies for a number of years. And it's great today that she's going to pull a bunch of this together for us all so we can see how these various projects are working. So we'll turn it over to you, Emily.
Great, and thank you very much. Can you see the screen?
Yep, it looks good.
Okay, perfect. Thank you. And so thank you very much, Lydia and Sarah, for inviting me to this webinar. It's great to be able to talk about 3 projects that have been going on for the better part of 5 years at USGS. And I want to note that all of these are representing a number of scientists, managers, stakeholders, other economists, and there's really a whole lot of work that goes into each of these case studies that I'll talk about today. So just so you know what's coming in this presentation, I'm going to talk a little bit about USGS's LandCarbon program and specifically about applications of LandCarbon. And there's 3 case studies: the Great Dismal Swamp National Wildlife Refuge case study. There, the big things are carbon sequestration, fire mitigation, and recreation ecosystem services. I'll talk about Ding Darling as another case study, and the Nisqually National Wildlife Refuge as a third. And all of these are in different points of research, and they give a good comparison of different types of habitats, different processes, and again, different points in the research. So a little bit about LandCarbon. USGS has a pretty large program that's looked at the national biological sequestration of carbon, largely using remote sensing. There are a number of in situ research projects. And specifically, there are a set of applications that get at site-specific research on carbon storage and flux to see how well some of those national assessment numbers really are. The applications are a partnership with the U.S. Fish and Wildlife Service National Wildlife Refuges, and they also attempt to address some of the management issues and talk and think about, if you managed for carbon sequestration, how might that affect some of the other ecosystem services or other things that you provide to visitors and to the refuge itself. And so a couple of those have included ecosystem service assessments. And as I mentioned, those are Great Dismal Swamp. That project is complete. Ding Darling, which is an ongoing project sort of in the middle, and Nisqually project, which was just initiated last year. So for all of these projects, we're using a pretty standard ecosystem services framework with a little bit of differences. Here, this diagram shows that black circle is your ecosystem, and there we're talking about quantity and quality of the different factors of the system. What's important in all of these studies is we want to consider how inputs influence that quality. So we'll usually be looking at a baseline study of the ecosystem, but then we want to look at what change does. So how do management decisions affect that ecosystem? How about climate change? What about factors outside of the refuge, for instance, upstream development? And how might that impact the ecosystem? And then flowing from that ecosystem, what are the services using the Millennium Assessment categories of provisioning, regulating, cultural, and supporting? And then we want to take those to kind of final goods and services, things such as clean drinking water, climate change mitigation, and also consider who are the beneficiaries. Are they just visitors? Are they global residents? Who actually is benefiting from any kind of change? So first I'll talk about the Great Dismal Swamp Project. And just for folks who aren't familiar, it's a forested peatland in southeastern Virginia and northeastern North Carolina. There's a map of the refuge on this slide, which is basically showing different types of systems, what types of vegetation there are, if it's water, where there are roads or ditches. And so there's been a lot of physical science happening on that refuge in terms of looking at local scale carbon storage and flux. And that includes things like biomass, measuring, remote sensing, looking at soil moisture, cores to look at carbon over time. There's also hydrologic research and a great model of the hydrology of this refuge. So one thing that's important to note, and this system is highly disturbed and has been subject to things like catastrophic fires over the last decade or so, but really it's been disturbed since the time of George Washington. So it's an interesting case study, and looking at restoration efforts is really important to both the refuge and as much as we can help from USGS. And so here the ecosystem services team was really tasked to look at what are the baseline services that are being provided, and then how might select management actions influence those services. This has a very large interdisciplinary, interagency, and even more team. Some of the important partners are Fish and Wildlife staff, especially the refuge management, who's very active in the study. The Nature Conservancy has been doing research there for many, many years. And George Mason, Southern Methodist, and Clemson universities all have research components there as well. And those are a couple pictures down at the bottom of some brave folks who are going out into the field to take measurements. And there is not a picture of me there because that's a little bit too bushy. So for folks that haven't seen this before, this is was an opportunity to do what I would consider a gold standard of ecosystem service assessment, in that we work closely with the refuge management staff. We were involved up front when the science was really being designed and initiated to potentially have influence, so that we could get some of those factors in ways that we could translate into economics more easily. And we also had a lot of stakeholder engagement from the very beginning. So what I'm showing on this slide is that we started off when the project was first kicked off by going to a group of stakeholders and asking them to prioritize the services that we would be actually looking at. And this included refuge management and representatives of visitors, representatives of communities that were just adjacent or downstream of the refuge. And so we had a pretty diverse group. And this was what they came up with. Biodiversity was number one. Wildlife viewing was really important. Education, nutrient cycling and flood protection, carbon sequestration, and fire mitigation. And so we had to pick a few of these to actually look at. We weren't able to look at everything. We did look at wildlife viewing. We incorporated biodiversity into that because we thought it would be a little bit challenging to look at biodiversity in and of itself. Education also we incorporated. We weren't able to look at that in and of itself. Carbon sequestration is something that we considered in each of these three projects, mainly because this is a LandCarbon project, and that's an important thing in terms of the science that's going on and partnering with that interdisciplinary team. And this one has a pretty interesting fire mitigation ecosystem service assessment. So here what I'm showing is a logic flow of carbon sequestration ecosystem service. And we developed these very simple diagrams mainly to talk with stakeholders and explain what do we mean by ecosystem services, how does habitat influence something that you might care about. So here what you're seeing, again, is a simple logic flow of the ecosystem. You've got biological sequestration in your vegetation. What's really important in the peatland is actually in the soil, and you may also have sequestration in the water. And that influences ultimately how much atmospheric carbon you might have, climate change over time, and can reduce damages in terms of health effects, property damage, loss of life, ecological functions, and lost agricultural yields. So we're using that last category, very commonly known as the social cost of carbon, to look at what is the actual value of this service. So for the carbon sequestration methods, and I'll discuss this in most detail for Great Dismal and not for the other two case studies, but here the biological sequestration was assessed by the science team using LIDAR and field validation to look at above ground biomass. So they're going out and measuring how big trees are and associating that with remote sensing data. And then they're extrapolating to the entire refuge, which is 45,000 hectares. There's also below ground biomass. So again, I mentioned that peat is really important. It's something like 80 or 90% of carbon sequestration in this type of system. And there they're doing cores to look at what sequestration is over time. And another important factor in that is the different types of vegetation can accrete or create more sequestration in the soil. So that's really important when looking at changes in vegetation and the different systems within the habitat. Excuse me. So there was an effort to model the entire system using land use and carbon scenario simulator, known as the Lucas model, which is a state and transition model, and it simulates carbon pools and fluxes over time. So this is a really great way to aggregate all of the information in terms of these are our different vegetation types, here's how things are going to change no matter what over time. And then if we can put on top of that, okay, you have a management action or a change to climate, how does that then influence those changes over time to give us how much carbon sequestration we might have? I mentioned that we use social cost of carbon. The interagency working group on social cost of carbon information was used, and we looked at the whole spectrum of discount rates over a 50-year period. So I mentioned the state and transition model. In this system, there were 4 vegetation classes. And again, these can have differences between above ground biomass of carbon, as well as how much they contribute to the peat soil itself. And so there's Atlantic white cedar and pine pocosin, which are those traditional vegetation types, and then things that have come in with disturbance like cypress gum and maple gum. And then wet and dry is important in this type of a system. So transitions will include things like a fire, a storm, drainage, those management actions like rewetting in this case where things have been dried out. There are ways to re-wet the soil, and ultimately you end up with a new state. And again, that's associated with a different amount of carbon. And so the types of things that can be changed in that state and transition model are, what are the vegetation quantities, what's the soil moisture, what's the disturbance, and then what's the management. So in terms of valuation, I mentioned the interagency working group on the social cost of carbon recommend looking at all 4 of the different discount rates. So they have a 5% discount rate over time, 3%, 2.5%. Those are all for average damages. and then damages at the 95th percentile, looking at 3% as well. So these values are in 2017 dollars for different years of sequestering 1 ton of carbon dioxide, excuse me. And so here, this picture shows you what the model itself does. And what you can see in 2015, which is our baseline year, is a picture of different colors that show what are the different vegetations. Again, those are all associated with different carbon sequestration rates. And then in 2065, so over our 50-year time horizon, you've got a new set of colors, and there's not a whole lot of change. This scenario was no management, so this is less than current management. And there's arrows that pop up that show a little bit of change. We're losing some of that pine picosin, which is, again, one of the endemic species that has more carbon sequestration over time. Now what I'm showing is a second scenario that's an extreme fire event. And in this case, we're showing 2 large fires that occur in the same area within 5 years. And what's really happening here are these blobs of blue. And that's essentially open water, where the vegetation has gone so much that open water takes over. And that's a really bad story for carbon sequestration. The fire is something that has occurred in Great Dismal. There were 2 what we call catastrophic fires, and I'll talk about those a little bit more in the fire mitigation service. But here what I'm showing are results of this carbon sequestration service. And here we ultimately had 4 scenarios. We had a no management scenario, no management with catastrophic fire, as I just mentioned, current management, so just what they're doing now and moving forward, and then increased management. This was sort of the, you have no budget, what would you do? And then what you'll see here are large bands in terms of carbon dioxide sequestered, and then the average. And those bands are representing essentially variation within the state and transition model that accounts for natural variability over time. But it's, you know, sort of what we expect. The more management, the more carbon is sequestered. In this next slide, I'm showing the net present value of carbon dioxide sequestered. And here, it's just adding a lot more uncertainty, again, using all 4 of those different discount rates. So you can see the bands become very wide as things add on to each other, but it's essentially the same story. Here you've got negative benefits. If you had no management, all of those are negative. So you have more emissions essentially, leading to, you know, higher social costs in both scenarios 1 and 2. And in scenarios 3 and 4, you're having positive anywhere, you know, on the order of $100 million per year. I'm sorry, not per year, in net present value, all the way up to, you know, over $1 billion in net present value. Again, that's for a 50-year time period. I also wanted to show the trend over time. For the most part, there's just natural fluctuation, which is showing up. But what's important in this slide is that catastrophic fire, the lighter blue line. When you have those fires, you have these huge drops in carbon. And that was really what we found out from this analysis, is that while the types of vegetation are important and accretion of peat over time is important, a catastrophic fire loses so much carbon dioxide at once that you just can't make up for it with accretion, essentially. So one of the things that we kind of work with management is that avoiding those catastrophic fires is the biggest bang for your buck. And so as I mentioned fire, let me move into the fire mitigation ecosystem service. And so this essentially is looking at very specifically this type of a peatland system where hydrology impacts the likelihood that a fire will occur. So in a swamp, the wetter it is, the less likely a fire is going to occur. The type of vegetation, so hardwoods versus less hardwoods, essentially, you're more likely to get, the hardwoods are more resistant. And another thing to note is that fire is a natural part of the system, and things like pine picosin actually rely on fire. But those are surface fires, which are short in duration and remain at the surface. When we talk about catastrophic fire, we're really talking about these deep burning fires that go into the peat, in cases many, many feet, and they can burn and have burnt over periods of 100, 120 days. And so there's really a big impact. So from the system's quality to next the fire probability, which could be either magnitude or frequency. And then ultimately, when we look at the ecosystem service in social terms, we're talking about damages reduced. So this can be air quality and human health impacts, carbon emissions avoided, as well as recreation and tourism losses. So to look at fire mitigation, we only look at that catastrophic fire. Again, it's defined as sufficient economic and ecological magnitude. But for the most part, we're talking about these deep burning peat fires. Something very different from, excuse me, a peat fire as compared to wildfires out west is that the smoke itself remains lower in the atmosphere just based on the way things work. And so in that way, it can be more destructive in terms of air quality. And so there are two high-level factors that we considered in the biophysical evaluation: the probability on an annual basis of a catastrophic fire, and then the effects. And again, I mentioned those effects that would be considered. And we focus on human health exposure. So to do that, we used a study that Rappold et al. At EPA conducted in the Picosin area, which is in northeastern North Carolina. So a very similar system, and they came up with a methodology to look at health impacts, and we essentially used that and did the same thing to look at Great Dismal Swamp. So it uses aerosol optical depth readings from satellite imagery, and that provides essentially your area of concern and duration of impacts. So we looked at fire from 2008, known as the South 1 fire in Great Dismal Swamp, looked at those satellite images to see, what counties might be affected and for what time period. And then we take this whole thing another step above and beyond what's been done before to look at what's the monetary value of those health outcomes. So you know what health outcomes are. Wildfire smoke exposure increases incidence of asthma, chronic obstructive pulmonary disease, pneumonia, heart failure, and cardiopulmonary symptoms. So there are certainly going to be effects that are not reported, but we do focus on those worst effects that would actually send somebody to the emergency room. And then in terms of valuation, we look at the cost of illness, and that's going to include actual costs like medical bills, as well as opportunity costs like lost wages and the value of time lost. It's worth noting that other studies have indicated a willingness to pay to avoid health effects to be substantially higher than the cost of illness. So this is a pretty good representation of a lower bound for what the actual social costs might be. So the results that we found at this point for a single fire, that those health effects were on the order of $2.2 million, and that's again for one fire. Annual probability today with the disturbed system is about 2%, or 2 of these events in a 100-year period. And I say that, but in the last couple of decades, they've actually had 2 of these catastrophic fires, so it may even be higher than that. So what we looked at is the historical probability is 1%, or 1 of these events every 100 years. With that assumption, we could look at an annual cost of illness as being worth about $44,000. So what we're saying there is if you could reduce that probability through rewetting, essentially because the dry conditions are leading to the higher probability of catastrophic events, that you could have a benefit of avoiding those illnesses at a social value of $44,000 a year. So we also didn't include other costs, things like reduced tourism. So during these fires, people in Virginia Beach were affected, restaurants were affected, There would be reduced recreation. People wouldn't be allowed access to certain parts of the refuge itself. And as I mentioned when we talked about carbon sequestration, there would also be huge losses of carbon that also can be accounted for. And so the takeaway there is management actions can reduce the risk of catastrophic wildfire. So another service that we looked at in Great Dismal Swamp is wildlife viewing. This is a really important service here as well. Essentially, you're looking at that logic of what's the habitat, what kinds of wildlife is going there. There's a lot of birds, it's a migratory pathway, and as well as this refuge is in an area with a lot of access to urban areas, so there's a lot of opportunity for recreation. So this is a pretty simple analysis. We look at actual visitation, and then we looked at those visitation rates just reported by the refuge staff. And what you see here is it's mostly wildlife observation. About 44,000 people every year come for wildlife observation. Photography is another category. And then there's a smaller number of people that come for fishing or hunting or other types of things. But overall, there's about 92,000 people visiting per year. And so we disaggregate fishing and hunting as a type of consumption from non-consumptive recreation. I also want to mention again that biodiversity is an important factor. So people are coming to this refuge to see specific species that they may not be able to see other places, and biodiversity really contributes to that, and we considered it as an intermediary ecosystem service in this wildlife viewing service. So we base the valuation on the travel cost consumer surplus, but essentially doing a benefits transfer. And we're using Fish and Wildlife Services 2015 survey for wildlife watching values. And we use both residential and non-residential values. And so the short story here is it's about an annual value of 2.7 million, mostly residential, and somewhat smaller non-residential. Again, like I mentioned, this is close to a number of urban areas. So residential visitation in terms of Virginia residents visiting is pretty high. So on that prioritization list, I also mentioned flood protection was something that stakeholders were really interested in. And essentially here, the logic is the wetland acts as a sink. It helps to reduce peak flows when there's a storm event. So this is not, where this refuge is located, it's not helping with coastal surge of any type, but just when you have rain, the downstream communities, they get less flow in their streams because the wetland is essentially working as a sponge. And this would lead to flood probability that's reduced, either in magnitude or frequency, and valuation would be based on property damage and safety implications. We did not end up assessing this one, but it's just one to mention that it's probably a service that's being provided by this and many other refuges. And then a final service that we didn't ultimately assess, but that was important to stakeholders, was looking at water quality and nutrient cycling of the system, and essentially the system's ability to act as a sink, especially with some agriculture that may be flowing from upstream of the refuge. The refuge may be capturing some of those nutrients and other pollutants before they then flow downstream and create problems along the coast. So as I mentioned, the Great Dismal Swamp project is complete in terms of the ecosystem service assessment and really provides the most comprehensive of any of the projects I'll talk about today. But the second project I'm talking about sort of in the middle phase, and this is looking at the J.N. Ding-Darling National Wildlife Refuge, a totally different system. This is a mangrove forest off the western coast of Florida on Sanibel Island. And so completely different system, different recreational draws, different types of sequestration of carbon. Again, the physical science going on there is local scale carbon storage and flux, and there's also remote sensing. And so to date, we've looked at ecosystem services in baseline, so what's there today and what they have. And we're really just starting off scenarios looking at exogenous factors. And this system, again, is being different. The management actions are not necessarily as broad, and a lot of the exogenous factors that we're considering are things like hurricanes or pollution that's coming from the mainland. So not necessarily within the control of the refuge, but things that they want to be thinking about to see if they can mitigate those impacts. So here for carbon sequestration, the methods are essentially the same as I described for Great Dismal Swamp. There is not quite as much physical science going on, but ultimately we'll have those carbon sequestration and we'll have state and transition modeling to look at that over time. And evaluation as well, we'll be using the same methods. We've looked at sea level rise protection in terms of coastal protection for storm surge and coastal erosion mitigation. Recreation is very important in this refuge. There really are many, many people that visit it. It's a pretty beautiful system, and it's one of those, again, that there's access to urban centers nearby. Other things that mangroves provide, commercial fishing can be important, pollution abatement, wood and timber, although that's not a service, they aren't able to use any of that, as well as aesthetic value. So people living nearby have a really beautiful system to look at. And so, yeah, we've looked at those first three. And so I'll just talk about sea level rise, ecosystem service, and what's been done there. There can be both wave attenuation provided by mangroves. This is pretty well documented as a type of ecosystem service for mangroves. Here you've got the mangroves dissipating wave energy to that habitat. What it's doing ultimately provides coastal protection from wind and small waves, storm surges, etc. And then you've got reduced property damage, loss of life, loss of agricultural yield as your final ecosystem good or service. So just as a scaling up, on average, mangroves provide about $3,000 per hectare per year in coastal protection. And however, we thought this might be something that was applicable to Ding Darling, but showing the map here, what you can see, the mainland on the right of Florida, and then Sanibel Island. So the tan area is all developed area, beautiful homes, beautiful beaches, and then the green refuge area is on the inside. So we ultimately assessed that it's not likely to help with waves. So your waves are going to be coming from the other side. So in this case, wave attenuation is not a likely service from the mangrove system. They may, however, protect from soil erosion and inundation. So as sea level rises, mangroves continue to accrete, and that can help stem that rise and how that might ultimately affect property values. So near Fort Myers, which is the mainland closest to Sanibel Island, Florida is estimated at 2.85 meters per year, plus or minus 0.49 meters per year of sea level rise based on observations. And then, so again, yeah, we expect the mangroves will have some ability to slow that down. So I mentioned wildlife viewing is really important service here. There's, again, a lot of birds, but there's also alligators, one or two famous crocodiles, and this unique habitat, especially in the United States, there are not very many mangrove systems, is a real draw. And before I move on, so we looked at that again in terms of using visitation numbers and benefits transfer, so I won't talk about that too much anymore. And then the final case study that I wanted to talk about was just initiated last year. And again, a very different system. We're talking about Billy Frank Jr. Nisqually National Wildlife Refuge. And so this is an estuarine system located at the southern end of Puget Sound in Washington State. So now we're traveling across the country to a system that's now influenced by saltwater and is estuarine, and again, very different from Ding Darling or from Great Dismal Swamp. And they've been doing, USGS has been working with Fish and Wildlife Service refuge management there for many, many years, I believe a decade, looking at different types of science, including food web energetics. So how does carbon flow through the food web, and what's happening to fisheries, and more recently looking at local scale carbon storage and flux. And along with our project, there are folks doing marsh equilibrium modeling, which will look at how does sea level rise ultimately impact the system, and how does it change the vegetation types here. So vegetation type here is a little different, things like tidal mudflats to open water, and then that's also associated with types of birds that will use the system, as well as fish. Another thing that's very different in this system is they did have a restoration project. I'll talk about that very briefly in a minute, but so that's already happened. And so looking at the change in ecosystem services post-restoration is part of our task with this. So again, here we're looking at baseline ecosystem services, and then ecosystem services going forward under a set of different scenarios. And so this work is really in progress, just starting. Anthony Good in the Science Decision Center is really leading the charge, and he's looking at the Brown Farm Dike removal that occurred. And again, that's the restoration project that has really changed the system, changed the flow of water, which ultimately changes the habitat. And he's pretty close to done with a hedonic price model here. And this is looking at how the value of houses that are near the dike and near the refuge changed when the dike was in place and then afterwards. And then another important thing that he's looking at is looking at salmon habitat in the Nisqually River Delta. And here he's working on a bioeconomic model, which will look at habitat associated with salmon that are coming from essentially the nursery, going out to the open ocean and coming back. And this is an important food source as well as commercial source for Native American tribe in the region. And there isn't that much recreational fishing within the refuge, but again, it provides an important service. And so he's working on that bioeconomics model, which will integrate ecology, resource biology, and economics of fisher behavior in the region. So all of those are just starting off. And we're also at the same time going to be looking at things like recreation, which is important in this refuge, and carbon sequestration. So our goal is to have that suite and be able to compare different services and provide an analysis of a portfolio of services. So as I mentioned in the beginning, all of this work represents multidisciplinary, multi-agency partnerships, and there's a long list of folks who are really imperative to any of these studies. Diana Hogan provides all of the leadership and the integration for Great Dismal Swamp Project, and many folks you see there, again, from USGS and partners. And Ding Darling, Ken Krause has really led the charge on that. And the Nisqually Project, Kristen Bird is the PI on that. And so I just want to acknowledge the contributions of all of these people, because the most important thing about all of these case studies is that they are being done in partnership. And as important as doing the economic studies of ecosystem services can be, doing them in isolation may not provide as good of information as these interdisciplinary projects. And the ability to work directly with stakeholders and refuge management staff helps these projects go from sort of academic literature to meaningful decision support. I want to mention a couple publications that are out. So Great Dismal Swamp has 3 publications available on just ecosystem services alone, and there's a much longer list of publications on all of the different science. And then finally, I want to mention that you may see about more of these at a Community on Ecosystem Services in 2020 in Florida. And that's the end of my presentation. I'm happy to answer any questions.
All right, thanks very much, Emily. We did record this webinar, and it'll be up on our website later this week or early next week if anyone wants to revisit any of the information that was presented. But in the meantime, if you do have a question while we have Emily on the line, please enter it into the chat box and I can read it off. But I can start us off. We have a couple questions here. And could you just talk a little bit more about how either the refuges or USGS plans to use this information?
Yeah, that's a great question. And so, for instance, in Great Dismal Swamp, we've provided this information largely to help look at if you did manage for carbon, does that impact your other ecosystem services? So for the most part, the information is looked at as outreach material. So one of the things refuges really have to do is help their neighbors to understand the benefits that are associated with having, for instance, a swamp next door. So it's an important tool for outreach and also an important tool for looking at, if we're going to increase our management actions, what ultimately are those social benefits that can be helpful internally for justifying, budgets of more management, and also considering, are there trade-offs between ecosystem services and those values? So that's the main things there would be for outreach and for helping to understand trade-offs between different management decisions.
Great, thanks. I have another question for you. I'm curious to know a little bit more about how you calculated the health costs, the cost of illness and other costs that you mentioned in the first example.
Yes, so we did obtain emergency department visitation numbers. So what Rappelled et al. Did is look at cumulative relative risk. So essentially they said, when there's a fire, let's just say there's 100 cardiovascular emergency department visits, and in surrounding areas there were only 70, so we're saying the cumulative relative risk is 30. So we did the same thing. We used those cumulative relative risk numbers and applied them to emergency department visitation numbers. So that's how we get essentially the physical quantity. And then the monetary value, the cost of illness, we use EPA's Benamap values. So they have regional, like in Virginia, the cost of this illness, and it's, per type. So for instance, for cardiopulmonary episode, this is the average cost of illness. And then we used, that also has typical loss of productive days. So for instance, if it's 2, we then applied the average wage rates for the counties for that. So that's how we came up with those values.
Great. Are those methods written up somewhere in a publication or anything like that?
Yes, yeah, that let me pull up, sorry, let me just pull that up. So
I was going to say we could post some of the related publications along with the presentation if you would share them with us.
Yeah, absolutely, and the lead author on that is Brian Partham, and yeah, all of those methods are written. It's here, and yeah, I can provide those as well.
Fantastic, thank you. Do you have a question, another one to ask, Sarah?
Yep, so someone's entered into the chat. Has anyone ever worked on ecosystem services of the Arctic National Wildlife Refuge versus the economic oil development there that you're aware of?
I don't believe that USGS has. I do believe there is something out there. I think there are some like environmental nonprofits that have put things out, but I'm not 100% sure, and I don't believe USGS has done anything on that.
Great. One more question. There were a number of services that you mentioned but said you didn't quantify or assess, and I'm wondering if that's something you're still planning to do at some point, or better understand like why not and what the barriers are to incorporating a broader suite of services?
Yeah, that's a great question, and really it comes down to scope, resources and time. So we really considered the flooding ecosystem services in Great Dismal was something we were trying to work out. It was just difficult to make the connection between the hydrology of the swamp and the potential to reduce essentially, flooding in adjacent communities. So we worked on that, but the connection wasn't strong enough. It was really the physical connection. So we aren't gonna go back to that. And then the nutrient cycling was pretty similar. We didn't have enough information, and there wasn't science being done on capture of nutrients in the system, so that we weren't able to do that. Really limited by both the physical science as well as just resources and time.
How have you been selecting the refuges that you work at? Is it sort of volunteer basis, or is it, trying to get a varied set that would be a sort of a more complete set of cases?
So the LandCarbon program has a strong partnership with the refuge system leadership here in headquarters, and it's a little. I'm not 100% sure how they came about with Great Dismal Swamp. A lot of it, I think, has to do with the refuge manager being very innovative and excited and having these questions about how management could change things. So that was really where things kicked off. And I think that, Ding Darling and Nisqually, to a lot of extent, are sort of opportunities that we're just taking advantage of. There's work to be done there that connected with enough science, and then there was enough interest in the ecosystem services that they were started in those two refuges as well.
All right, that's all the questions that we got. Thank you very much for joining us today. And again, we'll post all this online, the recording of the webinar, as well as links to some of the publications later this week. So thank you again, Emily, and everyone, please have a good afternoon.